Hello, everyone. Today I would like to talk to you. Today I'd like to present our defect spectroscopy work on perovskite solar cells. Firstly, I will introduce you to the different methods that we use, impedance spectroscopy and deep level transient spectroscopy, and then what are the different modes of DLTS that would allow us to characterize defects in perovskites. And later on, I will move on to our recent findings concerning the temperature-dependent ionic conductivity in perovskites and how we can access a capacitance-based method in order to obtain temperature or thermodynamic quantities such as enthalpy and entropy. And furthermore, how we can use these newly obtained parameters in order to understand the origin of the defect in the perovskite and also the location of the defect, whether the defects are forming in the bulk or the boundaries. So let me start the whole talk by introducing perovskites. So as many of you probably know, let me just briefly take a pointer. So as many of you probably already know, perovskite is a material that contains a calcium titanate structure. That means you have three different elements of different sizes organized in a specific manner. And in a three-dimensional picture, you can see it as a corner sharing octahedra in infinite space. So based on what material composition you use to fabricate a perovskite, they are called differently. For example, I have shown here there are the three ideal perovskite materials for which prone to lead to very high efficiencies. The first one is a MAPI. We call it MAPI. In a brief expansion, it would be methyl ammonium lead triiodide perovskite. So as you can see, it contains both organic and inorganic compositions together. So it's a hybrid one. So the second one is a pure inorganic perovskite, inorganic perovskite. And the third one is a much more complex one which is composed of three different cations and two anions, two halides together. Ideally, when every atom of these compositions are located at where they're supposed to be, there are no defects. We have a perfect crystal. But in real life, we don't have a perfect crystal. In any one of these atoms, when they're misaligned from their designated positions, we will have defects. And perovskites are known to have point defects, known to have more of a dominated by ionic defects, and said to be one of the reasons that explains the hysteresis in their recurves. So if you have such defects, in your material, such as vacant site or interstitial site, anti-site, and it doesn't have to be a point defect, it could be also a line defect where the whole atomic layer is misaligned from its designated position. It could also be grain boundary. So when you have such amount of defects in your material, all these defect sites can act as potential traps for the charge carriers. That means your charge carriers might fall into this trap and might not be able to contribute to the charge extraction and potentially limit the efficiencies. Which is why it's essential to characterize defects in perovskites, not only be able to identify them, but also be able to understand the parameters that govern defects. So this is what we are interested in. We try to understand how many defects you have and how fast they're moving in your material and where they are in your energy levels. And also recently we found that the defect density and the mobility are governed by two thermodynamic quantities, such as migration enthalpy and formation enthalpy. And activation energy is a combination of these two, and you can experimentally obtain them through impedance spectroscopy. I will get back to the details in the second part of the talk, but let's start with the basics first. So this is how a typical perovskite looks like, a solar cell looks like. You have an absorber material, which is sandwiched between hole and electron transport layers. When you don't have these electron hole transport layer deposition, you would have a homogeneous distribution of these mobile charges. But once you deposit these transport layers on top, you will have built-in potential induced in your device, which will push these mobile ion charges to the interfaces with respect to their charges, one charge will accumulate at one interface, another charge will accumulate at the another interface. So such charge accumulation would lead to Debye layers, which is nothing but a charge of certain density would occupy it for a certain length. And when you have such a Debye layers, you can, by using Debye model, you would be able to access the density and corresponding diffusion coefficients if you can detect these defects, these mobile ion defects. That's what we do. We try to understand how many of these mobile charges are in there and how fast they are migrating to the interfaces. So since we're talking about the mobile charges here, moving charges, you can do this by using capacitor-based methods. You can measure the capacitance by applying a tiny alternating voltage with a certain frequency and by measuring corresponding current signal out of it. And the ratio between both would lead you to impedance, or in other words, capacitance if you have a proper model, if you model your own solar cell in a proper manner. You can do it by using RC or in a resistant in a parallel configuration or in a series configuration, or the combination of both. So since the geometry, not only the geometry of the device contribute to the capacitance, but also the moving charges. So you can be able to detect the capacitance, the defect signal, the ionic defect signal by varying the frequency, because you vary the field and the corresponding ionic defects will also follow the field. If they follow the field, you would be able to detect it in your capacitance frequency signal. So that's what we do. We vary the field by varying the frequency. At very high frequencies, none of the charges will be able to follow the field. So you would see almost a geometric capacitance. And as you go on decreasing the frequency, the fastest ionic defect would will start to move. And at some point, it can't follow the field anymore. So you will see a constant capacitance value again. And when you go on decreasing the frequency, you would also, the slowest among them will move, and you will see corresponding capacitance step. So at the end of the day, when you look at the capacitance spectrum, each capacitance step would indicate one ionic species, a specific ionic defect. It will provide you the information containing one specific ionic defect. And the corresponding inflection points, which were shown here, these 2 points, would give you the migration rate. That means the rate at which the ionic defect will perform the jump from one lattice site to the other lattice site. And the corresponding capacitance step height will contain the information of the mobile ion densities. So that's one way of doing it. And this is a typical example of impedance spectra of a MAPI device. So as you can see, this is we measured until 510 kilohertz or so. And you see at very high frequencies a geometric capacitance. And as you go on decreasing the capacitance, the fastest ion, which we call beta, seems to move. And then as you go on even decreasing the frequencies, you would see the slowest ion contribution. In order to obtain a much more resolution of the data, we do the derivative of the capacitance with respect to frequency. That would lead us to such spectra. So potentially what we do, we look at the capacitance peak positions. We collect these points with respect to temperature for both defects. And when you plot them in one Arrhenius plot, which is nothing but these rates with respect to temperature, you would be able to say what is the activation energy, diffusion coefficient. And when you collect the capacitance step heights, these peak points, the Y component, from that, you could be able to say how many mobile ions with corresponding to one specific defects are in there. So this is in the frequency domain. You can also do this in a voltage, in a time domain, where you study the transients in a time scale instead of capacitance with respect to frequency. Instead of measuring capacitance with respect to frequency, you look at here capacitance with respect to time. So in order to do that, we maintain the frequency constant, and we study the perturbation of a small voltage, like 0 to 1 volt or so, into your device, and see how the transients relax back to its original position. For example, if you have the device here, once the transport layers are deposited, you will have the mobile ion charges which were accumulated at the transport layers because of the built-in field. When you apply the pulse, these charges will be pushed towards the bulk of the perovskite. And after a certain time, when the second equilibrium is reached, when you stop the pulse, these charge carriers will relax or retard back to their first initial equilibrium position. And the corresponding transient would contain the information of the mobile species. So if you look at the capacitance relation, it contains the geometric capacitance that comes from the geometry of the device, obviously. So it also contains the information of the capacitance step height, which would potentially lead you to the concentration of the charges, whatever that is moving. And it also contains the rate, emission rate in this case. And it's indeed possible, ideally it should be possible to say whether the absorbed charge is positive or negative. That's the advantage of DLTS in comparison to impedance. But the important thing here is you should be able to know, you should be able to know if the background charge, whether the material is p-doped or n-doped, that you should know. Once you know about the background charge, you can be able to separate positive and negative, or anion or cation. So this is just an example of our MAPI device, where we measured DLTS measurements with respect to temperature. And we varied between 200 to 350 Kelvin in 5 Kelvin step. And you see that here is the geometric capacitance. And there are two. So as you can see, the red ones are below the geometric capacitance, means that they belong to one specific charge, or whatever that is. The top ones belong to the opposite charge. Whatever this charge is, this belongs to the opposite charge. DLTS, it is, you might have two ionic species contribution in one single transient. So it would be a bit complex to evaluate the data like this. In order to evaluate it better, you can use an averaging algorithm such as boxcar approach, where you define a rate window and you try to see how the capacitance varies in the specific rate window. So what you potentially do is you define 2 points in a time scale, one here, for example, and you maintain this ratio between these 2 points constant, and you move along your transient. And you look at how the capacitance varies, like C2 minus C1, for example. So if you look at our DLTS boxcar signal, this is what you see. And these two are the capacitance contributions from T2 and T1. And what you do is you define a time constant containing these 2 points, and you move along whole your transient in this particular rate window. And by doing so, it would give you the possibility of looking at the whole transient with a specific resolution. So this plot represents the time constant everywhere, and the maximum of the time constant at a particular temperature would lead you to migration rate. So here we have shown you the boxcar representation of a typical MAPI device. You see there are 3 different defects, 2 at high temperatures, 1 at low temperature. And most of the time in MAPI devices, we see these 3. However, it also depends on the transport layer sometimes, depending on the MAPI composition you use. So so what we talked about is a capacitance transient. It's called conventional DLTS. You can also do this with as Dino said, there are different modes of DLTS that exist, depending on which transient you look at. You can also look at current DLTS. You maintain the same parameters, voltage, transient time, everything same. Instead of looking at capacitance signal, you look at the current signal. And it is possible to do so with the MFLI, MFIA, by using one of the oscillators you set the one of the oscillators to 0, and then you look at you extract the current data. So so here I have shown you two. Capacitance is represented with C and current is represented with I. As you can see, even with the different mode of current, mode of DLTS, you would be able to extract the same information. You can also do this with optical DLTS, so where you maintain everything same, except instead of applying a voltage pulse, you excite the device by using optical pulses. So if you compare both modes to capacitant DLTS, current DLTS seems to be more sensitive towards high migration rate defects because of the math goes into the relation. And optical DLTS, it's almost similar to capacitant DLTS. You change the field in the device and observe how the charges relax back to their equilibrium condition. So it's almost same. Just the excitation is, but your material doesn't need to be a p-n junction material in the optical DLTS. So, but as you can see, they're almost belong to the same regions, but also have certain amount of difference between them. So, in order to know whether all these three defects belongs to the same origin or they belong to different defects, to know that, we looked at in order to improve the resolution. We looked at, we defined a transformation function, and we applied the inverse Laplace transformation of it. That means you improve the resolution, but at the same time, the errors involved in the measurement also get enhanced. So in order to solve this, mathematicians at TU Chemnitz, they developed a regular a mathematical model. The details can be found in Sebastian's physical review paper. And what came out of it is that even though you see with different modes, you can access the rates, even the rates are a bit slightly different from each other, they all belong to the same defect distribution. So it is indeed possible to access the same information by using different modes of DLTS. So in order to understand whether our results are consistent with the others or not, we compared our results to literature. Here are reported, these results are reported for different configurations or single crystals and lateral dividers, for example. And what we found out was even though you use different methods and different configurations, all the measured rates are in the same range, indicating that even though you use different models, or different techniques, all lead to the same migration rates or emission rates in this case. And we see typically 3 different defects, and they seem to be consistent with literature. So briefly, to summarize what we saw so far is that there are 2 defects that are visible in impedance spectroscopy of a MAPE device, and 3 defects in DLTS. And even though the rates are a bit wider apart in different modes of DLTS, all belong to the same defect distribution. And these results are consistent with literature. So one of the observations we did while measuring multiple samples is that among these 3 defects that we saw, only 1 defect seems to be consistently present in many types of perovskites, and the 3 types of perovskite that we observed. And in order to understand the origin of it, we went further looking into the direction of conductivity. So before I go further into details into that, I would like to show you how our setup looks like. So this is our setup. We call it spider, given how it looks like. So we use MFLI with MFMD and IA options together, and we do 4-probe measurement. This is our pulse generator. In principle, you don't need a pulse generator to do DLTS. MFLI can be used as its own pulse creating source. And the optical pulses, we used a laser diode, which is somewhere behind here. And the light part comes from the bottom of the sample. This is the temperature controller, and we use a liquid nitrogen source to monitor the temperature. So this is potentially what our setups looks like. So as I said, 1 defect seems to be present in most of the perovskite that we measured, So in order to know what is the origin of the defect, whether this comes from iodide or lead or methylammonium or hydrogen carbon, to understand what it is, we extracted the conductivities. So if you look at the conductivity relation, it's a bit different to what you conventionally see. Normally, you get the conductivity of an ionic species through resistance of the created by the ion. But what we found out was conductivity seems to be depending on the time constant, regardless of whether you choose to obtain this time constant by measuring rates directly or through the resistance of the ion by using Nyquist plots. It both would lead to almost similar results. So, and we obtained these conductivities and we compared these conductivities with respect to stoichiometry, and we compared our results to the literature. For example, if you look at these two groups, Panzer and Meyer groups, who did the conductivity measurements with respect to iodide partial pressures and found that ionic defects or ion migration is dominant in perovskites in terms of conductivity, and the defect that they observed seems to be iodide because it followed the same trend as the decrease or increase the iodide partial pressure. They observed a similar concentration variation as well. So what we did is we compared our results to theirs, and as you can see, at this particular temperature, just as an example, they're almost identical. And when we not only compared to these two groups, but also several, you can find more information on it in our paper. So the bottom line here is that this defect that we observe in many perovskites seem to be dominant in terms of ion conductivity and seems to be commonly present in most of the perovskite. So this comparison to iodide partial pressure conductivities already indicated that this defect could be iodide-based one. However, in order to verify our theory, also validate our own results, we compared our migration rates measured at MAPI at different stoichiometric ratios to triple cation, so which is a complex system, and also at different concentrations. So that's what we did here. As you see, these are the MAPI data that I have been showing all the time. And these are the circular ones are the triple cation data, which has a very complex composition. Even though they have such complex composition, when you compare both the results, all the defects showed, all the rates showed similar range of values, indicating that whatever the defect that you're observing, that seems to be present in both of the materials. That still doesn't help us because we still don't know what the defect it is. So in order to eliminate at least organic part of the complex part of the organic composition, we measured cesium lead iodide, which is a complete inorganic composition. And what we saw was this defect seems to be also present in cesium lead iodide. That indicates that whatever the defect that we're observing seems to be present in all three types of perovskites, leaving us with the possibility of the defect being lead or iodide. So if you think about lead, it's heavy, probably, in most of the case, mainly requires very high activation energies to form the defect, so which might be the reason you might not see lead, which could be the reason that you might not be able to see lead as a moving charge. In other words, it's likely that what you observe is iodide. It's most likely that what you observe is iodide-related defect. So since we know that it's an ionic defect and what we are observing is an iodide, we try to understand this defect better by looking at the thermodynamic quantities. So if you think about a crystal, we have different atoms, and each atom are at their designated positions. And each one of them are connected to their neighbors through bonds. When you supply your crystal with a proper amount of energy through temperature or while you're fabricating your device, there might be a point where the neighboring bonds will break and the atom will become free of the neighboring bonds. And it will move to a certain location, leaving a vacant site or an interstitial site behind. So by the process of creating one defect, you will always form a defect pair, whether it's a vacancy pair or vacancy interstitial pair. So that's what we understood from the mobile ion density relation. So as you can see here, N represents the mobile ion density, which seems to be directly proportional to the formation enthalpy. So in other words, formation enthalpy is nothing but the amount of energy that you have to give an atom to be free of its neighboring bonds, to act as an ionic defect, for example. So, and you can access this experimentally by obtaining temperature-dependent mobile ionic defects. So what we did is we obtained the mobile ionic defects, defect densities by using Debye model. Now, this is the model we used. And we obtained the values with respect to temperature. You will obtain an Arrhenius plot. And from the slopes of these Arrhenius plots, you would be able to say what's the formation enthalpy of the defect. And this approach not only allowed us to access the formation enthalpy, but also gave us the possibility to access a new parameter that is called as we call it as total ionic defect density. So this is not the same as the mobile ion defect density because these are not only mobile ones, but also the immobile ones. So you have a certain amount of defects, not all defects are mobile. The mobile ones will be given by small n, and the mobile ones plus immobile ones, all the total defects will be given through this total ionic defect density. And you can access it by extrapolating your mobile ion densities to infinite temperatures. So this is also what we understood. And also we looked at the diffusion coefficients. As you can see, in order for an ionic defect to migrate from one lattice site to another lattice site, it has to overcome certain energy barrier. And that energy barrier is given by migration enthalpy. And on an average, if you look at the diffusion coefficient, it always contains activation energy. And this activation energy is a sum of both of these components, formation enthalpy, migration enthalpy. First, you have to form a defect in order to let it migrate. So that's why you always have to account for both of them. So that's what we did. We looked at temperature-dependent diffusion coefficients. That gave us the possibility to access the activation energy. We looked at the temperature-dependent mobile ion densities. That gave us the possibility to get formation enthalpy. Subtracting those lead us to separate both quantities. And by the end of this evaluation, we have three different new quantities to analyze. That is total ionic defect density, formation enthalpy, migration enthalpy. How can we use these three parameters to understand the ionic defects better? Towards that, we started looking into the total ionic defect density. As we discussed, DLTS indeed help us to separate the positive and negative charges as long as we know the background charge. If we know it's a p-type, p-doped, n-doped material, then we can separate. But in perovskite, we are not sure whether the given material is a n-type or p-type. We are not sure about that. So it's still debatable whether the polarity of the defect is positive or negative. So in order to solve this problem, we looked at the total ionic defect densities with respect to the stoichiometry of two different perovskites. So this is what we did. So as I've been talking about, we looked at two different perovskites, MAPI and triple cation, and we looked at the difference in the total ionic defect densities with respect to stoichiometry. So as you vary the stoichiometry, you can expect certain trends. For example, when you increase the X composition here, or MAI composition, you could expect more amount of methylammonium iodide interstitials, or iodide interstitials. But what we saw was a decreasing trend that indicates that whether the defect that we are seeing is either methylammonium vacancy or iodide vacancy. Since we observed this defect in inorganic perovskites such as cesium lead iodide as well, this can't be methylammonium. So it should be iodide vacancy. We also did the similar analogy in triple cation as well. This is the stoichiometric ratio. As you go on increasing the concentration, you would expect an increasing trend in methylammonium interstitial or iodide interstitial. Also, as you go on decreasing one, decreasing the concentration, you would expect increasing trend in iodide vacancies. So this also indicates what you see is an iodide, but are we seeing a transition from a vacant site to an interstitial site? Because impedance cannot distinguish between the charge. It can only measure the moving of charges, or there's something hidden. This we cannot answer yet. But what we can say is it is indeed possible to understand the origin of the defect by comparing the stoichiometric variation, the total ionic defects with respect to the stoichiometric variation. And that's what we did. And it appears that what we see is an iodide-based defect, iodide-related defect, and seems to be a vacancy in the MAPI device. So that's one. And the next point that really bothered us a lot for a while was the order of magnitudes. So in a crystal, when you already know how many atoms you have and the volume of the unit cell, you can calculate theoretically how many atoms per centimeter cube you can have, right? So if you compare to that, since we already know it's iodide, we calculated the theoretical atoms per centimeter cube density, and we compared it to ours. And our values are at least 4 to 6 order of magnitude smaller. And we wondered why. Are we really looking at the total ionic defect densities, or there is something hidden? And we digged a bit deeper into the literature, and what we understood was it's lower because the mobile ion density not only depends on total formation enthalpy, but also depends on the entropy of formation. So you always have entropy compensation so that you at least can have part of the crystallinity maintained. That means, so C iodide belongs to the total atomic density, which can be calculated theoretically. And if all the atoms are mobile, then you wouldn't have a crystal. It will become a liquid. And this entropy is the key that holds together your crystal. That means at least part of the atoms are where they should be, so that at least you can form a crystal. Based on that logic, we estimated the entropy, and remarkably, the values that we obtained are exactly in the expected range for KCl and NaCl, which are alkali halides. And in metals, you would expect less than 1, but in alkali halides, you would expect such high range of values. This also supported our result of, or our theory behind assigning this defect to iodide or halide component. So that's one of our key results. And the other one was, since microstructure plays quite important role in perovskite efficiency or in defect dynamics, we compared all our thermodynamic parameters to the grain boundary area or the grain size. So as you can see, this is the enthalpy, this is the mobile ion density, this is the total ionic defect density, which is nice that we can separate both of them, and entropy, and this is the grain size. And what we observed was they all follow the same trend. For example, if you look at the formation migration enthalpy here, when the grain size is highest, all these values are highest. That means when you have bigger grain boundary area, you have to apply more amount of energy to a defect in order to form the defect, in order to migrate the defect. That indicates that your defects are migrating at the boundaries. However, what we cannot answer is where the defects are forming, because we varied the grain size as a function of, as a consequence of varying the stoichiometry. So we are also intentionally inducing the defects. So we cannot say where the defects are forming, but they seem to migrate at the boundaries. So under the assumption that defects are also forming at the boundaries, we can say that defects are migrating at the boundaries. Also, how these parameters influences power conversion efficiency. So if you look at here, the 3.04 is the highest efficiency device. And this highest efficiency device seems to contain lowest amount of total ionic defects and lowest amount of formation migration enthalpies and highest amount of entropy. So this can be considered as a benchmark for high efficiency, because if you go back, here in the entropy relation, if you have a perfect crystal where n equal to 0, your whole entropy will become infinite. That means the more absolute entropy you have in your crystal, the more ordered your interface would be in terms of the measured defect. So to see whether our finding is true or not, we also did the same thing for triple cation as well with respect to stoichiometry, and we observed the similar trends. However, the variation that we did is very small in terms of grain size, so we cannot really pinpoint that this is the case. So in order to verify and validate our own evaluation method, we are looking at single crystals, which has an infinite boundary. And we're also looking at the lateral devices at the moment, which has a smallest grain boundary. So by doing so, you will have two boundary conditions and you can validate the theory. So that's what we are working on at the moment. So to summarize my talk, so far we saw that there's one defect that seems to be dominant in many perovskites, in 3 different perovskites, and it seems to be the iodide vacancy. It is indeed possible to obtain the thermodynamic quantities by using impedance spectroscopy, and you can separate mobile and immobile ionic defects by using this evaluation method. And for the highest efficiency device, it seems to be that you have less amount of total ionic defect and smallest formation migration enthalpies. And under the assumption that the ionic defects are also forming with the grain boundaries, we can say that they're also migrating at the boundaries, which is in this theory is a work in progress, but seems positive that we are in the right direction. With that, I came to the end of my talk, and I would like to acknowledge our group at TU Chemnitz and funding from DFG. And I also would like to thank Tim and the whole DLTS user meeting team for having me, and you all for your attention. I'm open for questions.